from a company called Smart Fibres, and I'm going to present to you today the recent developments we've made about acoustic events location based on the FPG monitoring system. So just a few words about Smart Fibres. We've been around a while, since 1998. We are based in the UK, and we are exclusively specialized in optical sensors based on FPG. In the market where we are working are mainly oil and gas, where we've developed a distributed pressure sensing system, and we are also doing some machine condition monitoring for subsea assets. We are also working on the aerospace market for doing some detection for landing gear, and also with embedded structure health monitoring on embedded application, mainly UAV, if you have been following a bit this week. And also we are active in wind energy with the blade load monitoring system. So about this demonstration, so we are introducing an FPG-based acoustic events detection. So it's based on the instrument which is sitting on the table, which is called Smart Sonic, which is an interferometric phase measurement system. And the point is to provide an alternative to conventional distributed DAS systems which are performing acoustic sensing. Originally it was developed for subsea condition monitoring coupled with hydropump, and recently we decided to use it for acoustic emission detection. So the principle is on the graph on the bottom of the slide. So we've got a fiber coil, which is actually the sensor, which is bonded on the asset to monitor, and the acoustic wave is coupled to the coil. The coil is delimited by two FPG, which are FPG1 and FPG2, at two different wavelengths. And the instrument is performing phase measurements on each FPG. And the difference between these phase measurements is analog to the acoustic wave, which is coupled to the fiber coil. So in terms of expected performances, so the resolution of the system is below the nanometer in terms of fiber length, and taken on conventional fibers, which can allow a strain up to 1%. That's given dynamic range, which is around 158 dB, which is comparable to that system. Obviously, it depends on the length of the fibers. And the bandwidth is quite important for acoustic events. So at the moment it's working with 200 kilosamples per second, but we are planning to increase it to 1 megasamples to detect ultrasonic wave. And obviously the bandwidth is limited by the sensor itself and the coupling to the asset. The major point, again, that system is the distance, so we are not limited by the distance between the sensors and the instruments. So in terms of technology benefits, so obviously the distance from the sensor to the instruments. Although we are fairly polarization insensitive, we believe we've got a good placement bandwidth, good dynamic range. The challenge would be to multiplex fibers together, which we believe is doable by system design. And also we've got all of the benefits of any FPG system, like the ETEC certification, the cost of the instruments, and the possibility to perform embedded flight. So the next, I'm going to the demonstration. So what is on the table is it's a simple carbon fibers composite panel. We've got the core of fiber, which is the blue things you may be able to see on the panel. And we've got the two FPG which are in the box. The goal of the FPG is only to provide a reference. The end goal is to use the FPG as another sensor, like accelerometer or temperature sensing, and to use the coil of fibers between the FPG as the acoustic sensors. And what we are going to demonstrate today is an acoustic event generated by a fencing break. And we'll show you we can get a decent SNR from this system. Okay, so the instrument is here. The sensor itself is in this blue package, and the FPG are in the box. And the box is connected with a single fiber to the instrument. time domain signal, which is sorry. You can see the time domain signal, which is in nanometer, which is the variation of length of the fiber coil. The bottom graph is a frequency domain signal, and I'm just going to generate acoustic events. So this graph on the top right is a threshold based on an acquisition based on the threshold, and this is my events. Can generate another one a bit further. We can detect it with a quite decent signal to noise ratio. I said about 40-50 dB above the noise floor. Thank you.
Thank you very much. So our next presenter